see what we get. Any question about this? Any question? Any questions so far, please? Okay, I'm going to define the following two vector fields on SO3. X is some omega tilde 1. X is a function of x, right? It's linear in x. This is a matrix, and remember x is also a matrix. X is a point, little x. Do you want me to call this little x R to be things to be clear, or you find as little x? Little x are the coordinates of your manifold. My manifold is space of matrices. So this little x is a rotation matrix. Do you want to call it R, or you are fine with just little x? Any preference? Okay. So this guy is a vector field, and this guy, again, is another vector field. So here my rigid body is moving with an angular velocity omega 1. Here my rigid body is moving with an angular velocity omega 2. Okay. You just defined if something called some cool mathematical operation called B bracket. If I'm giving two vector fields, we can get a third vector field out of that, right? So what is the Lie bracket between x and y? Well, it's partial y, partial little x's, times your x, minus the other way around. This is very easy to get. Okay? Okay, let's see. This is easy because each large x and y are linear in the little x. So what is partial y, partial little x? Little y. Partial y, partial little x is simply omega 2, correct? Just bear with me for a minute, please. This is omega 2 times large x. So this is omega 1 tilde times x. I'll put the x outside. Minus the other way around, so it will be omega 1 tilde, omega 2 tilde. Okay? Okay, look at the following. Look at the following. Well, if this is a vector field in SO3, I know for sure that this guy is a skew-symmetric matrix. And I know for sure that this guy is a skew-symmetric matrix. Why? Because I'm given this statement. Both are tangent. Okay. When I do one of these operations, this guy only, I know that the result is not in general tangent, which in our language here, the result is not necessarily skew-symmetric. So this guy is not little SO3, this guy is not in SO3. Which means when you do play around with your matrices, if you start with any two skew-symmetric matrices, you multiply them together, and the result is not necessarily skew-symmetric. But what about this? I know for sure, because of differential geometry now, I know for sure when I do this operation, the result is a vector field. The result is tangent. Which means now for my rigid body, it means that this matrix is skew-symmetric. Which means that if you have any two skew-symmetric matrices, any two skew-symmetric matrices, and do this operation, the result is indeed has to be a skew-symmetric. Okay? So this is a very easy proof that given omega 1, omega 2 skew-symmetric matrices, omega 2, omega 1 minus the other way around is indeed a skew-symmetric matrix. Let's have it more practical. More practical. I will start with omega rho. My body has 3 degrees of freedom. Let's just remember the roll, pitch, and yaw. So the roll is about x. Here is x. Here is y. Z downward. Okay, this is the standard notation. Roll is like this, okay, about x. Pitch is about y, like that, okay, and yaw is about z. So I will start with omega roll by 4 radians per second. This is some possible velocity in my system. My rigid body can surely roll. And omega pitch is maybe 3 radians per second in the pitching direction, about y. This is about x, this is about y, okay? Okay. Well, each one of these has a corresponding tilde thing. Right? 0, 0, 0. This guy's omega 1 is 4. I'm going to substitute over the tilde thing. So this is negative 4, 0, 0, 0, 4, 0. And omega pitch tilde is the same thing. 0, 0, 0. 3 is the 2 thing. This is 3, 0, 0, negative 3. Any questions so far? Any question? I know for sure that omega, the Lie bracket between the roll and the pitch, is what? On this definition, what we get is omega pitch tilde omega roll as matrices multiplication simply minus the other way around. Okay? So omega pitch times omega roll, this is, let's multiply this guy with that guy. So you get 0 here. Then what do we get? We get 12 here. Maybe I don't care about the rest. It's maybe zeros, that's fine. I want to get this guy. This is really 0. Okay? You can see this is not what?
It's not
It's not skew-symmetric, right? Minus. By this, by that, what do you get? You get 0. Of course you get zeros, that's fine. But then, so this is zeros. And then you will get here 12, magically. So the result is, this is not skew-symmetric, this is not skew-symmetric, the result is indeed skew-symmetric. That's fine. Skew-symmetric, and what do you mean by skew-symmetric? What do we mean by skew-symmetric here? Well, you identified your tangent space as the set of skew-symmetric matrices. So this guy lives in your tangent space, which means what? Which means it's an admissible velocity, it's an allowable velocity for your system, right? This guy has to be equivalent to some velocity matrix or vector. Indeed, it is corresponding to some velocity matrix whose vector is what? This is the 3, right? So 0, 0, negative 12. So if you do a Lie bracket between the roll and pitch, you get an equivalent velocity in the yaw direction. Well, now we can talk about practicality. Why? Sometimes your spacecraft or your robot or your submarine, you don't have an actuator to move you in the yaw direction. Or if it's a ship or whatever, maybe it's too heavy to do the yaw motion directly. Either you don't have an actuator, either your actuator in that direction is too weak because your inertia is too high, or you had an actuator but now it's broken down, it's not working anymore, okay? but still you have two other actuators. One create roll and one create pitch. You don't have a direct control authority to do the yaw. Yet this analysis shows you that, well, you know what? Even though you don't have this guy from the beginning, you just started with these two, this proof shows you that this is an allowable motion that you can do using these two only. How is that? Well, here is my system. I want to yaw for 90 degrees, for example, but I don't have a direct way of doing it. I just know how to do roll and pitch. What's roll? Roll is like this. What's pitch? Pitch is about this y-axis, right? Roll 90 degrees, pitch 90 degrees, roll back negative 90 degrees. The end result is yaw 90 degrees, right? And actually this leads to the following question. Well, you should need an existence thing, which is, you're saying, if these are two actuators, possible actuators, then there exists a way of generating the yaw motion. Okay? But how I will actually do it? How can I, well, if I have two velocity vectors, that's okay. But when I do this basic mathematics, I get a new velocity vectors. Velocity vector means it's allowable, it's doable. And I really like it. Well, you know what? I want to do yaw. How can I do yaw? In other words, how can I move along the velocity coming from a Lie bracket? If this is an actuator, I will turn on my actuator. If this is an actuator, I will turn on my actuator and turn off all the others. But this is not an actuator. This is combination of the two. Okay, how can I use them in combination to generate this cool guy? Well, here is the theorem that tells you how to generate the motion along the Lie bracket. Any questions so far? Any question about this? So, a surface with two vector fields, the result Lie bracket with this cool mathematical operation, this very weird mathematical operation, indeed has to give you a tangent vector to the surface at all points, for any surface. For a rigid body, if you start with two admissible velocities and do a Lie bracket, the result is indeed an admissible velocity. Okay? Whether or not you have an actuator to do it. Whether or not you have an actuator to do it. And we showed how we can do a 90 degrees yaw just by rolling and pitching. So we always try to shun away from nonlinearities. Whenever we have nonlinearities, we just try to linearize and neglect the nonlinearity in our system. But there are situations where the nonlinearity really helps you, that you can exploit the nonlinearity. This is one situation. Here is a theorem. Hope that I have a plan to show an example, but at any rate. Given x and y on gamma m, they are vector fields. Given point P in M. Okay. This way. Yes. vector field, the vector field gives you arrow at each point, right? In a smooth way, continuous way. You cannot do abrupt things. So this actually invokes the following question. Well, if I have a particle here and let it flow with the flow, where will I go after 10 seconds? So I will flow with this vector field, and I'll arrive at this point after some time t. Okay? So the map, this is, we started with some vector field x. The map that takes an initial point in the manifold and flows along some vector field large x. For a time t, it's called the flow map. This is maybe 7 now. The flow map. So it takes a point on the manifold and returns you back a point on the manifold. So the flow map of vector field x for time t. This is vector field on n. This flow map, we call it like this: phi t large x, and takes little x naught. So phi is a map that takes points on the manifold, returns you back points on the manifold, right? So how do I get this? How do I get this map? Given a vector field. Given a vector field, how can I get this point? Starting from that point, I want to flow along that vector field for time t. What's the resulting point? Well, actually, let's get hold of that curve, right? So this whole curve, was it its velocity vector at any point? At any point, its velocity vector is what? At any point, its velocity vector is what?
Tangent surface.
It's tangent, but I can have many tangent vectors. I'm particularly flowing along the prescribed vector x. So at any point,
Gradient.
this is indeed x at that point, right? Okay? So this is the integral curve of x. You want to flow along x. What do you mean by flow along x? I mean, I'm going to have a curve whose velocity vector is the velocity vector dictated by this guy at that point. You can call it gamma, you can call it little x's,